In this video, I'm going to talk to you about motion under the influence of velocity-dependent drag forces. And those would be forces of the form F vector equals minus kv vector. So the force is opposite the velocity and proportional to the magnitude of the velocity. In some cases, we also study forces which are proportional to the velocity squared and negative opposite the direction of the velocity. That's what this symbol means here. V hat means the direction of the velocity, minus means it's opposite that direction, and the V squared means that it's in the direction, or that it's proportional to the velocity squared. This can also be written as minus k times the speed times the velocity vector. But for the most part, we're just going to handle the minus kv. So let's think about an object that starts from rest. So at t equals 0, v is 0. And you have a ball. And when it's at rest, the only force on it, as it's released, is gravity. Once it starts to fall, however, as it's increasing speed, gravity remains the same, but there is now a small upwards force, kv, opposite to the velocity. So the acceleration is down, the force is opposite to the velocity, so the velocity is increasing, but it is not increasing as quickly as it was before. And at some time later, I get to the point I have gravity down, and this kv force keeps growing. If the mg vector is longer than the kv vector, then the acceleration is still positive. And finally, once the kv vector, the drag force, equals the gravity force, the object has reached what is called the terminal speed. The reason it reaches this terminal speed is because once the kv drag force equals the gravitational force, the acceleration is 0. The net force on this object is now 0, and it cannot get any faster. And to solve for that terminal speed, k times the terminal speed is equal to mg. So the terminal speed here is mg over k. So quick review, the initial velocity is 0, so the initial drag force is 0. Then it starts to move. It now has a drag force kv and a downward force mg, but the net force is still down. It's smaller, but it's still downward. It's speeding up. Here it's still speeding up because kv is not as big as mg. When kv equals mg, it reaches terminal speed, which we have calculated to be mg over k. Memorize that. That's a good thing for you to remember. So this equation is true only after it's reached terminal velocity. But what equation is true? What equation describes its motion up until the point where it reaches its terminal velocity? That's the goal of this video, and that's what we're going to solve for. And we start by saying, okay, acceleration is equal to the sum of the forces divided by the mass. And the forces on this are mg downward and kv upward. Divided by the mass equals the acceleration. So mass times the acceleration is mg minus kv. And at this point, we can't quite solve for the velocity because the acceleration and the velocity are related by the derivative. So we have to substitute in the fact that the derivative of the velocity is the acceleration, and we get the equation m dv dt equals mg minus kv. And that is a first-order linear differential equation which we need to solve in order to find the velocity as a function of time. Okay, I had to clear a little space there so we could do more derivation. Here we have the equation again, m dv dt equals mg minus kv. This is a differential equation because it has the velocity and its first derivative. So it's your first exposure, for some of you, if you're not in post-calc topics, to differential equations. And in this case, it is first order. It is first order because this is the first derivative. And it is linear because it's not v squared, it's just v. And we solve this by the method of separation of variables. The two variables here being the velocity, which changes with time, and time. So clearing this out a little bit, m over k dv dt equals mg over k minus v. I have now cleared out what's in front of the v to make it easier to integrate, because I know I'm going to integrate because I have a dv dt here, and I need to get rid of that. Then I'm going to separate the dv's from the dt's. So I'm going to multiply well, actually a couple of steps of algebra in a row. dv over this quantity, mg over k minus v, is equal to dt times what's in front of the dt, which is k over m. Now that is the separation part. That's what so far all I've done is separate. Now I need to integrate. So the integral dv mg over k minus v equals the integral of k over m dt. Now I need to put limits on my integration if I want to do I can't remember the word for it right at the moment. Definite, that's it, a definite integral as opposed to an indefinite integral. So I'm going to start out when the velocity is 0 and go to where the velocity is my v final function. Start out when t equals 0 and go to some final value t. So the integral, or the antiderivative, of dv over mg over k minus v, well, this is basically like 1 over v. Only not really, it's 1 over negative v. When you integrate 1 over v, you get natural log. When you integrate negative 1 over v, you get negative natural log. So this is the negative natural log of mg over k minus v. And because I'm doing the definite integral, I have to do from 0 to v. And that's equal to integral of k over m dt is just k over m times t, evaluated at 0 and t, which just gives you km over t. So plugging in over here, first I plug in v, then I plug in 0. So negative natural log of mg over k minus v minus, here's my first term, second term, negative natural log of mg over k minus 0 equals, plug in km over t, k over m times t, I mean, minus this with a 0 plugged in, which is just 0. So now the rest is just math. In fact, after this point up here is where all of it is math. This is where the physics is done. Now we have to do the math. So we did the calculus part, now we have to do the algebra part and a little bit of natural logs and stuff like that. So let's rewrite this a little bit. I think what I'm going to do, since I know what the answer looks like, is put the minus sign on the other side. So I have the log of, and wait for this fraction, mg over k minus v, mg over k minus v, over mg over k. This minus sign and this minus sign go to the other side. I have negative k over m times t. Now I have the log of something equals something else, and to get rid of the log function, you basically take e to both sides of the equation, because e to the log of x equals x. So on this side over here, it's mg over k minus v over mg over k equals e to the negative k over m times t. Simplifying even more, let's go back up here. We have mg over k minus v is mg over k. times e to the negative k over m times t. Or, rearranging even more, v over here, this is negative on this side, so imagine it goes to this side and then I just flip the equation around. But anyway, then that equals mg over k minus mg over k e to the negative k over m times t. Or mg over k times the quantity 1 minus e to the negative k over m times t. And that is the velocity as a function of time for the falling object falling under the influence of gravity downward and a velocity-dependent force backward. And if I plug in at t equals 0, then v equals mg over k times 1 minus e to the negative 0, which is 1 minus 1, which is 0, which we know. At t equals 0, velocity is 0. If we plug in t equals infinity, v equals mg over k times 1 minus e to the negative infinity. E to the negative infinity is 0. 1 minus 0 is 1, so I just get mg over k, which is quite gratifying because that is what was on the earlier page equal to the terminal velocity. So at the beginning, I have a velocity 0. At the end, I have the terminal velocity. And in between, I have this function here that is 1 minus e to the negative k over m times t.